Hello everybody and welcome to today's workshop. My name is Michaela Oberle from the life science business of Merck KGaA. My presentation is addressed to all thin layer chromatography users who are using only classical normal phase HPTLC so far. Today I would like to give you more information regarding the benefits of modified high performance layers to increase the separation quality of your analysis. My presentation takes about 20 minutes and it's divided into two parts. In the first part, I will give you some basic information about the different layer modification and how to select the right one. In the second part, I will show some examples and advantages around modified layers. At the end, there is time for questions. Before I start with my presentation, I need to mention a legal information. So the life science business of Merck KGaA, Darmstadt, Germany, operates as MilliporeSigma in the US and in Canada. Now let's begin with a brief overview of the history of thin layer chromatography. So all starts around 1900 with the discovery of chromatography by Zweig. Then a very active phase appears with the first aluminum oxide solvents for chromatography and the development of paper chromatography. So the next milestone was in 1955 with the standardized silica gel developed by Stahl. In the 1916, first pre-coated layers appears on the market. And with the development of 5-micron silica gel materials in the 1917, the age of high-performance thin layer chromatography starts. So in the 1918s, HPTLC modified layers were developed. So first the reversed phase, then the amino, followed by the cyano and diol phase at the end of the 1918th. Some years ago, the development of hyphenation aspects came up and the linking from HPTLC to other analytical methods increased. So for example, the HPTLC MS coupling. But still today, around 80% of HPTLC and TLC is performed on normal phase silica gel layers. So only around 20% is performed on modified layers. So on this slide, the comparison of TLC to HPTLC layers is presented. So the normal basic TLC plates have a format of 20 by 20 centimeters and the particle size are much bigger than on HPTLC layers. As I said before, the particle size is reduced to around 5 micron and the plate format is 20 by 10 centimeters. So that therefore, the development or migration distance is reduced to 2.5 and also the time. So HPTLC is much faster compared to TLC with a very high separation performance. But the performance is not only increased by the switch from TLC to HPTLC layers. The performance of a separation is essentially determined by the selection of the right stationary phase and the corresponding mobile phase. But it's often not so easy to find the right separation conditions when so many parameters can influence the separation quality. So a very helpful tool is the triangle scheme according to Stahl to select the right separation conditions. So by rotating the inner triangle in the wheel, one selected parameter at the applicable position automatically defines the other parameter. So in the absorption chromatography on the left picture here, to separate an unpolar lipophilic analyte, the stationary phase should be active and the mobile phase should be apolar. So like dissolves like is a principle for the partition chromatography, shown here on the right side. If you know the chemical structure of your target analyte, and you can easily define the polarity of your solvent. For separating lipophilic substances, the stationary phase needs to be lipophilic and the mobile phase polar. The same principle also fits for acid and base. Acid should be separated with acid solvents. Base are best separated by using modifiers with a basic functional group or an appropriate amount of ammonia can be added to the solvent mixture. So optimal chromatograms can be obtained by variation of these parameters for a particular separation problem. When the high-level conditions are defined, a look on allotropic series of solvents is helpful. In this table, the solvents are listed in order of increasing elution power, and it's helpful for choosing a suitable mobile phase. Another helpful scheme is a solvent triangle of Snyder, where the different solvents are grouped according to their polarity, dipole moment, and the acid-base character. Single solvent groups are suitable for special layer modification. So an overview of the available layers is given on my next slide. In general, all layers are suitable for all substances, and the separation is related to the solvent mixture. If a compound is hydrophobic, so with a positive log p value, then the use of a reversed phase is recommended. For lower polar analytes, you can switch to a normal phase. If there is too much retention, for example, on a reversed phase or RP18 phase, then sometimes it's worth to try a shorter chain length, so like an C8 or C2 chain. So if there is not enough retention or a poor quality separation on the RP18 or a normal phase, then try something in the middle. So like a diol, cyano, or amino phase. These are mixed mode phases. Also for very high hydrophilic substances, it's worth to try, for example, a cellulose or an impregnated plate for chiral substances. So here are listed some examples of substance classes or examples which fits very well to these different layers. One I would like to highlight here with the cyano phase. It's also possible to do very good two-dimensional separation. So this means you can use the cyano phase to do first in one direction separation with a normal phase solvent, and in the other direction you use a solvent mixture you normally use for reversed phase. So then you get the best separation conditions of both sides. There are also more advantages for using these modified layers, and this I will show you in the later examples. As you can see here in this example, sometimes it's better to switch the stationary phase. So here we have the same application. So UV filters are separated out of a cream matrix, and on the left side on a normal phase silica layer, and on the right side we switch with the same sample to a reverse phase, RP18 phase, and the separation is much better, and the bands are sharper. Also, the used solvents are in with reversed phase separations mostly, I would say less harmful. So here we have a mixture of methanol, acetonitrile instead of toluene heptane. So not only the solvent mixtures are much simpler for reverse phases, a further big advantage is the lower influence of water from a sample on the chromatographic system, because often water is one important part in the solvent for reverse phase. This example shows the influence of the water content in the solvent on the retention of the plasticizers on a RP18 layer. The influence is much lower than on normal phase system, which is shown in the next example. In the upper part of the diagram, you can see the minimal change of the RF values of all four substances over the humidity range from 0 over 20, 50 to 80% relative humidity measured on the DO layer. In the lower part, the change of the RF values of the same four substances and the same humidity steps on a normal phase silica layer. The result shows clearly that there is less influence of the relative humidity during the chromatography on the RF values on the diol modified layer than on the unmodified silica layer. As I said before, in reverse phase systems, mostly a high amount of water is used in the solvent mixture. So, but due to the polar surface of the RP18 phase, this can cause sometimes problems. So, because the layer is not wettable with a high amount of water. So therefore, special blades like the RP18W plate is available. So this means that it is highly wettable with water. This example shows the same application on the normal RP18 layer compared to the RP18W layer. And you can use here up to 100% water in your solvent mixture and have here in this example much lower migration times for the separation. On the next, the high amount of water in a solvent mixture increase the migration time dramatically, so that the separation is stopped, and so the diffusion increase and the separation quality decrease in this case. So on a RP18W phase, so this is not the case, and you can use this therefore for solvents with high amounts of water up to 100%. On this slide, an example of the separation of a substance mixture on RP2, RP8 and RP18 layer is performed. So for this unpolar substance, the separation quality increase with the chain length of the layer modification. And here I have an example of a very well separation of proteins or digested proteins on an RP8 phase. So the performance here is much better than on a RP18 phase. So for proteins, peptides, or for example benzoic acid, the RP8 phase is recommended. And here you have an application example on a RP18 phase. So this was shown before. So it's the determination of UV filters out of a sun cream. So a very high matrix loaded sample. And this example I choose because you can see here that we are able to measure then the mass out of this substance spots directly from the layer. So why should we use this special modified layers for our separation? So yeah, it offers us specific conditions to find the best separation condition to our special separation problem. So the layers are less polar than classical silica phases. They close the gap between the classical phases and the reverse phase layers. So they are well suited for the separation of hydrophilic or charged substances. And they allow us to use a normal or a reverse phase system. So it's more flexible, and all kind of solvent systems can be used. So especially the cyanoplate allows us to do two-dimensional separation. So normal phase mechanism in the first direction and the reverse phase mechanism in the second direction. So here is an example on a cyano layer with different mobile phase systems. And you can see with different systems you can also speed up your separation, or you can increase the separation quality. This example shows the separation of a steroid mixture on this both under this both conditions. So, and then I have another example on a diol modified layer, and here we have an example with steroids, and especially the diol modified layers is suitable for the separation of steroids, herbicides, or fungicides. So on this slide, some facts about the amino-modified layer are summarized. So the amino-modified layer provides a weak basic ion exchange characteristic, which helps in some separations. This unique feature enables the separation of charged compounds such as nucleotides, purines, pyrimidines, or phenols. So you can also use a simple eluent mixture for the separation. And one very big advantage on this layer is that you can use this for a reagent-free detection. So especially for sugars, you only have to heat up the plate, and the sugars react with the layer, and are detectable under UV light, or you can see it by a brownish or yellowish color. An example of such a separation is shown in on the next slide. So here a mixture from or samples from cakes and biscuits is shown, and here the sucralose is separated out of this high sugar matrix, and with staining reagents, and also with the thermic reaction with the plate, the sugars can be detected. On my last slide, I will give you a short overview of the use of cellulose plates for a special analysis of polar substances. So here we have different qualities available, and so typically, very polar, high polar substance can be very good separated on this cellulose plates, so such as amino acids or carbohydrates or phosphates. And also here a two-dimensional separation is possible, and you can do amino acid fingerprinting, for example, or metabolic studies. I hope I could inspire you to choose. I hope I could inspire you to try out some other layer modification besides the normal phase to solve your analytical problem and to increase your separation quality. And if you want to learn more about modified layers, or find application examples or detailed information regarding the different layers, please feel free to visit our web page, so sigmaulrich.com, and there you can find all information. So now I'm at the end of my presentation, and feel free to ask questions. Thank you very much for your attention.